Hello, I am Dwayne Gibson, a Field Applications Engineer for IAR Systems. I'd like to take a few moments to show you the IAR Systems Embedded Workbench product. For this particular demonstration, I will be using the IAR Embedded Workbench for ARM version. However, much of what I will show you today will be consistent across the many and various iterations of the IAR Systems Embedded Workbench product line offering. After the installation of the IAR Embedded Workbench product, all the features are set to their default and initial factory settings. When you start up the Embedded Workbench for the first time, you will see the Information Center for ARM or for your designated architecture be displayed. Let's start by taking a quick tour through the Information Center. First, you will see our Product Explorer. Here you can discover how to use basic and advanced product features. Our Products Explorer provides tutorials that are divided into different parts. You can work through all the tutorials as a suite, or you can choose to go through the tutorials individually. The tutorials call the printf library function, which calls low-level write function part of the runtime library. This works in our IAR CSPI simulator. But if you want to run the tutorials in a release configuration on real hardware, you must provide your own version of these functions depending on the library that you are using adapted to your hardware. Next, we have the IAR User's Guides. Here we provide detailed information about how to use various tools, and reference information can be found in the user's guides. Next, we have example projects, example applications that demonstrate hardware peripherals for specific devices and evaluation boards. I will come back to this topic in a few. Next are the IAR integrated solutions. IAR Embedded Workbench integrates seamlessly with the state machine tool IAR Visual State, as well as industry-leading real-time operating systems and middleware. Our successful RTOS partner program provides a broad and comprehensive development tools ecosystem of RTOS and middleware products, all highly integrated within the IAR Embedded Workbench product. Next, we provide hardware solutions. IAR provides a broad range of starter kits and in-circuit debug probes to assist in your evaluation and design. The links will take you directly to the IAR page associated with the starter kits or the IAR in-circuit debug and trace probes. Next, we have our support and user interface. If you have problems using the IAR tools, there are several resources for information that can be useful. Documentation and tech notes, as well as direct links to our support portal, are available here. Next are the IAR release notes for the given version of your IAR for Workbench installation. In this example, again, the IAR Embedded Workbench for ARM version 8.50.5. Here we have important highlights for versioning. We have important information that's provided by version, along with release notes regarding the individual components that has been updated, as well as any product package installations that we've modified or added to include new device support. Lastly is the IAR My Pages interface. The IAR My Pages interface will take you directly to the IAR My Pages. Here you can download product updates, manage your license, and update your contact information or check for your support and update agreement statuses. So, as mentioned earlier, let's take a deeper dive into the IAR Information Center for ARM Example Projects tab. Once inside the example projects, you will see a listing of example projects that can be downloaded. My screen is a little different from what you will see upon a fresh installation, as I already have an installed example project. What you will be able to notice is that you can download all of the examples at once utilizing the green circle with a white download arrow, or you can download any specific supplier partners example projects that you wish. This will save space on your hard disk drive. In this example, I'm going to go ahead to choose to download ST Microelectronics examples. If I hit the green download arrow, I will get a dialog box that will ask, where do you want to get the example projects from? I'm going to choose download from the IAR Systems server. If you have installation media, you can choose to download it from there. Once the download has began, you will see a progress meter showing you that a download is occurring and that is then extracting and being installed into your C program data uh, file on your C drive. What this will allow you to do is to always preserve a golden copy of those example projects. You will see here in a few more minutes when we actually go into an example project and create it, what I mean by that. While that is downloading and extracting, I'd like to explain to you a couple of other things. Oftentimes we get questions from customers that says, I don't see an example for this particular device. I don't see an example for this particular architecture. So, as you can probably see, we work with all ARM vendors. From the ARM 7, 9, 11, all ARM Cortex-M, Cortex-R, and Cortex-A architectures that are 32-bit. It would be virtually impossible to provide an example project for all of these architectures for all of the possible derivatives of evaluation boards and all of the possible derivatives of silicon packages, flash sizes, and memory densities. Therefore, we rely upon our silicon partners such as STMicro to provide SDK examples that will work within the embedded workbench for ARM. Perhaps in another video, we will showcase install, how to obtain and install these types of examples outside of the Information Center for ARM example projects directory. Once the download is complete, a dialog box will pop up indicating for you that your download has been completed and will be installed into the Embedded Workbench for ARM example projects subdirectories. And now you can see we have a newly installed example projects for ST Micro. So let's dig deeper into the ST example projects. If I click into the ST example projects, you will see a green arrow that will take you to information about those particular projects. However, let's go deeper one more level. Let's look into the STM32F4 as I happen to have an evaluation board for that particular device. Looking into the STM32F4 device, you will see several of the hardware solutions that IAR Systems provides. We have the starter kit indicated by -SK. We have our Academy boards indicated by -ACA and our -EXP Explorer board. I happen to have the Academy board, so let's utilize its examples. Clicking into the Academy board, you'll see that we have examples for capacitive touch buttons, LED light effects, a Morse code reader, and USB HID. There are two columns. The information column, which will open up a text file that explains the application and any relevant settings on the hardware, and an Open Project button, which will open the project in our Embedded Workbench workspace. Let's open the Light Effects project. Clicking the icon that looks like the Embedded Workbench icon, we'll get a dialog box to open that will ask us to choose a destination folder. In this particular example, if you recall, I had mentioned saving a golden copy of the project examples. This dialog box will allow us to locate the project in an arbitrary point on the disk that is not where the installation directory are of the examples. That way, if we mess up something, we always have the golden example to go back to. So I'll just utilize this directory that it's currently in, the IAR Embedded Workbench, and I'm going to create a new folder by the name of ST Micro. I'm going to select the ST Micro folder, and what you will see is the workspace will then be loaded with the application example. The information for ARM Center example is open. You can then navigate to the README docx file if you want to open it from within the project itself, or as I mentioned, the information tab, open the Information Center for ARM text evaluation of that exact same project. So you can see the description, the compatibility and what's required, the configuration of the board, and the getting started. Inside of the workspace, what you will notice is that we have the project as is embolded. Making a little room here on the window, I'll show you and navigate through our workspace directory structure. At the very top level, you will see what we call groups. The groups contain a number of C source files, and under each of the group, if you expand the C source files, you will then see the associated header files. In the project, under the workspace window in the project, you will see various project configurations. This particular project happens to have a flash debug configuration. Utilizing the drop-down, you can see if there are other configurations associated with your project. In this example, only the flash debug are listed. I will show you how to create other project configurations later in the video. Let's navigate some of the project settings and project options. You can reach the project options by highlighting the embolded project, right-clicking on the mouse button, and select Project Options. Or alternatively, you can select the Project tab and choose the Options menu. Or alternatively, on your computer, you can press Alt and F7 and it will open up the project options. Under the project options, we have two locations. One is the category location. The other are the configurations for that particular category. So let's look at the general options category. Under the general options category, you will see the device that was selected for this particular project, the STM32F429II. You may, in some examples, have created a project from scratch, in which case you can select either the core device if you don't know the particular project, or you can select down to the specific device. So to show you the listings under core, you can see the ARM 7s, the ARM 9s, the ARM 11s, as mentioned, the ARM Cortex-M, the Cortex-R, and the Cortex-A complex units up to the 32-bit. We're going to stick with the device configuration that was selected from the project originally. To the left of the device configurations, you will see a dialog box that will allow you to search for any other supported devices. So in this example, should the STM429II not give you the package type that you're wanting to really use for your production environment, you can select under the ST category to go to the STM32F4, and you will see all of the derivatives that are offered for the F4 and subset F429. Here are the extended packaging and memory options available for those particular devices. We're going to leave it where it was, just showing you that. Other things that you may wish to consider on the General Option tab are your library configuration. You may choose different types of libraries that are offered There are normal, full, and custom libraries. You may also wish to utilize a CMSys library or a DSP library from CMSys. Let's look at the C++ compiler options. Here you can choose under the Language 1 tab C language or C++ language. You can also choose your C dialect, C89, or standard C, allowing for C++ inline semantics or allowing for VLA structures. Here you can also choose if you wish to implement any type of Misera application checking. We can set the Misera options originally in the General tab for Misera C and enable Misera C, and here you can see which checks are listed and which are not. We're going to leave these as all as the default settings. Another tab that you may wish to consider is the Output tab. Uh, Perhaps when you are in production, you'll need a file such as an S record or a hex file or a binary image file. And under the Output Converter category, you can select Generate Additional Output. That will allow you to select different output formats for your files. Some are listed here: Intel hex, raw binary, or some of the more common ones chosen. We're going to just leave this unchecked for now. Next, you may have various build configurations that you require. You may need to call external tools or add in other additional files, and you can add those under the custom build. Under build actions, perhaps you want some files to be built prior or post the rest of your C file structure. You can choose those build actions here in the pre or post build command line. Under linker, we were going to use the standard linker configuration file for this particular project that comes out of our toolkit directory. Should you wish to use a different linker file, you can navigate to it here, or you can edit your linker file here. There are library options. If you wish to include other libraries to be linked into your project, you can include them here. Some customers also wish to name an output file. By default, the Embedded Workbench for ARM generates an output file. It is typically the project .out as a name. Under the list, we will also generate a linker map file. Another important category is your debugger category. Here under debugger, I have selected the iJet debugger driver. However, we have several other debug drivers to choose from. Should you happen to use the onboard SimSys app located on many of our silicon vendors' evaluation boards, you could select it here. There are also options for the ST-Link and other proprietary type interfaces. I'm going to choose the iJet in this particular example. The run to main feature is also checked in our debugger, as our application will initialize and will halt at the main function entry point. I will show that to you in a few more minutes. Next, if we want to verify the download through the debugger, we can select to enable Verify Download. We are using flash loaders in this particular example to locate our image in flash on the STM32F429. So we will use the flash loader. The toolkit directory contains the flash loaders. You can use different flash loaders should you wish, depending upon the project and the application requirements. We have other options listed, but another one that's typically used are plugins for RTOS and middleware. You can see the many selections that we can choose to plug into our application, from FreeRTOS to MicroC OS2, ThreadX, and others. In this particular application, we are not using any RTOS. The next category tab that you will want to look at is specifically under the driver that you've chosen. In this example, I've chosen iJet. This will allow us to set up the user interfaces and configure how the iJet debug probe will interact with the target hardware. In this particular application, we're going to set up and utilize the reset during connection. We're going to also power the target from our iJet probe. In this particular example, this evaluation board has the ARM Cortex MIPI 20-pin header. Pins 11 provides target power from the debugger. we're going to leave power on after debugging. The interface in this particular setup is going to be serial wire debug. Other options are JTAG or the proprietary CJTAG often used by vendors such as TI. There's also trace functionality. In this particular example, should we wish to utilize trace for a device that does have an embedded macro cell trace or a micro trace buffer or an embedded trace buffer, we can also do so here. The IAR iJet provides and the CSPI debugger provides some additional capabilities which can be discussed in other videos. Here, we're going to choose to leave the serial wire output protocol set at auto. And we're going to use, but there are options for Manchester or UART protocol for wider bandwidth handling. You can also see that the CPU clock interface is set at 168 megahertz. Under breakpoints, there's nothing for us to do here, but you can also utilize software breakpoints or hardware breakpoints in your particular example. I'm going to go ahead and say OK, as that concludes the general options setup for this particular project. Next, you will notice that there are some red dots associated with the groups and the associated C source files in your project. These red dots indicate to us that these files, C source files, have yet to be compiled into an output image. Earlier, I had mentioned that there is a method to configure other project configurations. If you wish to configure other project configurations, please choose Project Edit Configurations. A dialog box will come up. You will see that the current configuration is Flash Debug. Should we choose to make a new configuration, you'd hit the New button and name your configuration. We'll call this Flash Release. And we'll base this configuration upon the Flash Debug configuration, but set the factory mode to release. And we'll say OK. Now you will see the new configuration established as Flash Release. If I now say OK, I can utilize the new creation of Flash Release, and you will see in the drop-down two configurations, one for Flash Debug and one for Flash Release. This could happen if you wish to change any of the project options, linking configurations, build actions, or any other setup variables within your project. You may wish to create and test different configurations for different runtime reasons. Maybe you're running out of RAM. Maybe you're running out of flash. Maybe you're linked in different libraries. These are all examples of what you could use. Let's look at the main.c file for this particular project. In the main.c file, you will notice that there are in your workspace editor an option to look at different functions within the project. Here you will see the different functions associated with the project. There's a delay function, there is a main function, and then there's a decrement timing delay function. If we click the main function, it immediately moves our highlighted cursor to where in the program the main function is. Associatively, if we click any of the other functions, it will take us into the project where those functions exist. Also, just navigating within the main.c file, if you hover over a variable, you will see it light up. To understand more about that particular definition or variable or reference, you can go to the right click and go to the Go To Definition. And what you will see is a C file that will open up explaining that particular definition. So in this particular case, we wanted to see what the unsigned integer 32 types were defined at. Those were defined in the standard integer.h file. Or if we wanted to see something like where the systic is configured, we can go to the definition of where systic is configured. And that will open the core underscore cm4.h file. And here we can see how the systic is configured. This concludes the first part of the Getting Started with Embedded Workbench. I hope that you enjoyed the presentation. Please join me for section 2, where we will download and debug this particular application.